Gauss's law is a technique for calculating the electric fields of highly symmetric systems. When you have a charge distribution that has a symmetry or has a specific symmetry, for example, the charge distribution is spherically symmetric or cylindrically symmetric or planar symmetric, then we can use Gauss's law. But before we proceed, let me define the concept of area vector. So for example, I have a surface here, an arbitrarily shaped surface that sits on the xy plane. This surface can be represented by a vector whose direction is perpendicular to the plane of the surface. So apparently for this case, one points to positive z hat and the other one points to negative z hat. So an area vector has a magnitude of the actual area of the surface we are talking about, and the direction is the vector that is normal to the surface. When we have an open surface, we have two directions. One is from positive z hat and negative z hat. But to generalize this direction, we could just call this as n hat, because we can project this surface on the xz plane and then it will have a direction of n hat that is similar to y hat and so on. So again, we need the concept of area vector to calculate flux or electric flux. Again, area vector defines a vector whose magnitude is the actual area of the surface and it has a direction that is normal to the surface. So if we have a curved surface like this, its direction is not uniform, meaning to say, for example, this infinitesimal portion of this area has a direction pointing this way. When you visualize the direction of the infinitesimal area or portion of this surface, it has a direction that points this way. And apparently, if we try to look on the other side of this surface, like for instance this one, it has a direction that points this way or negative n hat, because it's going downwards. So for example, you have a cube. If you have a closed surface like this, then by convention, the positive n hat points from the inside of the volume going to the outside. So the positive n hat here points radially outward. When you want to represent the area vector from the inside, then it will have a direction of negative n hat. So the purpose of this area vector will become apparent when we begin calculating the flux or the electric flux. Next, let's discuss electric flux. So electric flux is a quantitative measure of the number of electric field lines passing through a surface. So imagine you have a surface and you have some vectors going to the right. Imagine this bunch of vectors are electric field. The area of this surface is represented by capital A. Flux is represented by capital letter Greek letter phi. And if this vector fields or bunch of vectors are electric field, then we could just put a subscript of E here. So if we have a magnetic field represented by vector V, then we will replace this with letter B. Electric flux is equal to the dot product of the electric field vectors with the area. So apparently the magnitude of electric flux is EA cosine theta, where the angle theta is the angle between the electric field and the area vector. So if we have an irregular area, so it has an area vector that points this way and this way. A uniform electric field passes through this surface. The proper way to calculate the electric flux through this surface is by dividing the surface into infinitesimal element and then calculating the dot product from each infinitesimal element. So for example, let's focus on this one. The flux at this small portion is equal to the electric field dotted to this small area vector. If we want to calculate the electric flux throughout this entire surface, then we just need to integrate both sides, and electric flux is equal to E dotted to dA. Now the dot product here is crucial because the orientation of the surface has something to do with the magnitude of the electric flux. So I have a surface, and obviously its area vector points this way, and an electric field pointing to the right passes through the surface. Then obviously the electric flux is greater if there are more electric field lines passing through the surface. Electric flux is directly proportional to electric field. Also, if you try to increase the area of this surface, then more electric field lines will be able to pass through that surface. This equation is consistent with the fact that electric flux is directly proportional to the magnitude of the area vector. Let me rewrite the electric field lines here. If the surface is parallel to the electric field lines, then obviously almost no electric field passes through that surface. We must be able to quantify the effects of the direction of the area vector and the electric field lines. And notice that when the area vector is parallel with electric field lines like this one, then electric flux is also maximum. So this kind of behavior is mathematically described by a dot product. Let me rewrite the definition of electric flux. So again, electric flux is the quantitative measure of the number of electric field lines or electric field vectors passing through a surface. Flux is actually a general term in physics wherein it describes the number of vector field lines passing through a surface. This vector can also be magnetic field. It can also be simply the flux of water molecules in a pipe and so on. Imagine I have a positive charge and there is a closed surface, an empty cube. Notice that when we draw the electric field lines coming from the positive charge, some of the electric field lines will be able to pass through this surface. But notice that the number of field lines passing through this side of the surface is also equal to the number of field lines that is getting out of this side of the surface. So in other words, when there's no electric charge inside a closed surface, so for example, let's focus on this side. If this side of the cube has an area of A, and apparently since we defined that its direction must be radially outward, then its area vector direction points this way, n hat. And the electric field passes through the surface like this, coming from the positive charge. So its electric flux is negative EA because the direction of n hat is this way. We have EA cosine 180 degrees, which is negative 1. That's why we have this value. Let's now turn to this side of this closed surface. So apparently, if I redraw this surface, the electric field lines points this way and the area vector n hat is parallel with the electric field lines. Therefore, the flux on this surface is positive EA. So if I try to calculate the net flux, so assuming that the flux on the other sides of the cube are 0. So for the total flux or the net flux is equal to phi sub 1 plus phi sub 2. Again, I'm not going to write the other flux for the other sides of the cube because they are obviously 0. Because it will result to an area vector and electric field lines that are perpendicular to each other. So it will result to cosine 90 degrees. I'll just assume that they are equal to 0. the other four sides of the cube. So again, phi sub 1 is negative EA and this one is positive EA. So they are equal to 0. So obviously, if there's no charge inside a closed surface, the net flux of electric fields passing through that closed surface is 0. I have again a closed surface like a cube. And this time, there is a charge inside that cube. Now, in order for me to calculate easily the flux that passes through this surface, I'll just assume another kind of surface that is symmetric with the charge. So this time, again, if I have a positive charge and it is enclosed by a surface, and this time I'm going to use a symmetric surface like a sphere. Surface is centered at the origin and the charge is also centered at the origin. Now the surface is at a distance r from the origin. So if we want to calculate the flux passing through this sphere due to this positive charge with a total charge of Q, then we write flux is equal to E dotted to dA. Now note that this is a closed surface, so we have this notation for the integral sign that if we want to calculate the contribution of a closed quantity, whether it's a closed volume, closed curve, or closed surface, we write a circle on the integral sign and we just designate it with S, meaning to say that we are integrating throughout the entire closed surface. If this is just a simple closed curve like this, then we replace S with C to designate it as a closed curve. Now obviously, each dA here on the surface has a direction that points radially outward, the same as the electric field lines coming from the positive charge. So basically, each infinitesimal element of the spherical surface experiences a uniform electric field coming from the positive charge. So I can technically put this electric field outside the integral sign because it is uniform throughout the entire spherical surface. And obviously the dot product between them, so if I focus on this small region, we have dA, an infinitesimal portion of the spherical sphere that has a direction of n hat, and the electric field that passes through this small area is also parallel with n hat. So their dot product will obviously result to a magnitude that has a cosine 0 degrees because they are in the same directions. I'm not going to write cosine 0 since it is equal to 1. And remember that dot product results to a scalar quantity. So the flux is equal to electric field times the area of the entire sphere is 4 pi and the radius is r squared. And the electric field of the point charge is equal to 1 over 4 pi epsilon naught q over r squared. Again, this is the electric field that passes through the surface at a distance r. Okay, this is the value of the electric field here times the area of the surface, 4 pi r squared. So notice that 4 pi cancels out and the r squared cancels out. So we end up with q over epsilon naught. Remember that this q here is the enclosed charge by the surface. So flux is equal to the dot product of the electric field and the area, which is equal to the enclosed charge over epsilon naught. And this is the simple form of Gauss's law. Gauss's law tells us that the electric flux passing through a closed surface is equal to the enclosed charge divided by epsilon naught. Gauss's law states that the electric flux through any closed surface, we also call this closed surface as the Gaussian surface, is equal to the enclosed net charge divided by the permittivity of free space. So mathematically, the flux is represented by the Greek letter capital Phi subscript E, which means that we are monitoring the electric field lines passing through a surface, is equal to the integral of E dotted to dA. And this surface must somehow enclose the charge distribution, and it is equal to the charge enclosed divided by the permittivity of free space, epsilon naught. Again, E here refers to the total field lines that pass through the Gaussian surface. And these electric field lines can come from both inside and outside of the Gaussian surface. So it depends on the position of the charge. Next, dA here, or the integral of dA here, refers to our imaginary surface called the Gaussian surface. And finally, the Q enclosed here refers to the charges or bunch of charges enclosed by the Gaussian surface. So let's have some demonstration. Using Gauss's law, we can now easily calculate for the electric flux due to the presence of different charges. So for example, if we have a positive 3 microcoulomb of charge enclosed by this surface, then using Gauss's law, the electric flux is equal to positive 3.0 microcoulomb divided by epsilon naught. As another example, what if we have a negative charge inside a closed surface like this, and it has a value of negative 1.0 microcoulomb, then the electric flux is equal to negative 1.0 microcoulomb divided by the permittivity of free space. Again, this permittivity of free space is equal to 8.85 times 10 to the negative 12. So you could just simplify this. What if we have a negative and positive charge outside this closed surface? As I emphasized earlier, the only charge that matters in Gauss's law is the enclosed charge. So basically, the flux that passes through this closed surface is equal to positive 2.0 microcoulomb divided by epsilon naught. How about this one? So there are a lot of other charges outside the enclosed surface, and we also have negative 2.0 microcoulomb that somewhat passes through the enclosed surface, and yet it is outside the enclosed surface. In cases like this, we calculate electric flux by just focusing on the enclosed charges. So in this case, the enclosed charges are negative 3.0 microcoulomb and positive 5.0 microcoulomb. So the electric flux that passes through this blue enclosed surface is positive 2.0 microcoulomb divided by epsilon naught, because the net charge inside this closed surface is positive 5 microcoulomb plus negative 3.0 microcoulomb. From one of our previous videos, we found out that the electric field due to a thin wire is equal to lambda over 2 pi epsilon naught 1 over r, and its direction is radially outward from the wire, which means that it has a direction of r hat. Now, we were able to calculate this electric field using a very arduous technique of integration, but we'll try to use Gauss's law to calculate this same electric field. So again, for example, we have this long thin wire, and it possesses a total charge Q. If its total charge is Q and its total length is L, then its linear charge density is equal to lambda. And if we just calculate for some small portion of this wire, for example, from this point to this point, small l, if that small portion of length has a charge of small q and a length of L, then it has a linear charge density equal to Q over L. So to use Gauss's law, we enclose this with an imaginary surface. Now, the surface we are applying here is obviously a cylinder because it must be symmetric with the charge distribution. As much as possible, the Gaussian surface must be symmetric with the charge distribution. This Gaussian surface encloses the portion of the wire that has a length that starts from this point to this point. So we wish to calculate the electric field at point P, that is a distance r from the wire. And this imaginary Gaussian surface, let's just say that it has a length of L from this point to this point. So to use Gauss's law, let's calculate the total flux. So obviously this cylinder has this area here and another area here and an area along the curved side of the cylinder. Let's just designate the flux on this area as phi sub A and the flux here as phi sub B, and the flux on the curved side of the cylindrical Gaussian surface as P sub C. So obviously, the total flux on this Gaussian surface is P sub A plus P sub B plus P sub C. Now obviously, for phi sub A, if we assume that this is a very long wire that extends from positive Z to negative Z, then the electric field lines coming from this wire is radially outward. Therefore, if we calculate the dot product on this area A, it's actually equal to EA cosine theta, and the angle between the normal vector of area A and the electric field line. Remember that the electric field lines are radially outward. The electric field lines coming from the wire are radially outward. Therefore, this is equal to EA cosine 90 degrees. Okay? Because the area vector is perpendicular with the electric field lines. The same goes for area B. So, the flux on area A and area B are both equal to 0. Next, for the curved side of the cylindrical Gaussian surface, we have electric field times its area, then cosine theta. Now notice that from this figure, the area vector on the curved side is parallel with the electric field lines radiating from the thin wire. So basically, this is equal to EA cosine 0, which is equal to just E times A. So the flux is equal to the electric field of the thin wire and times the area of this curved side of the cylindrical Gaussian surface. Apparently, the area is equal to length times width. The length of the curved side is L times the width. The width is this part. So obviously, it is equal to 2 pi r. Now, based on this equation, the total flux is equal to the flux sub C, which is equal to E times 2 pi r L. Now, using Gauss's law, this is equal to the charge enclosed divided by epsilon naught. If this enclosed charge has a length of L, remember that this point to this point is enclosed by a cylindrical Gaussian surface with length L. So basically, this charge has a length L. Now, to calculate the enclosed charge, we just multiply this L with the linear charge density. So this is equal to the enclosed charge. So this enclosed charge is lambda L epsilon naught. Let me write it here. E 2 pi r L equals lambda L over epsilon naught. And the magnitude of the electric field is therefore equal to, this length here cancels out. I'll end up with lambda over 2 pi epsilon naught 1 over r. And since the electric field lines are radially outward, this is r hat. Notice that this is the same equation that we were able to derive using integration from the previous video. We were able to derive the same equation using Gauss's law. This time, let's use Gauss's law to derive an expression for the electric field at the surface of a conductor. So imagine we have a solid conductor of any shape. So initially, this solid conductor has a zero charge. But if we populate it with a bunch of charges, for example, this one. So since this is a solid conductor, these free charges has a tendency to move throughout this volume. And assuming that they have the same charge, then each of them will experience a repulsive force from other charges. Therefore, if they will experience repulsive forces, they have a tendency to move away from each other. So eventually, when they reach electrostatic equilibrium, those charges will accumulate on the surface of the conductor. Now, if these charges are positive, apparently they cannot move away or outside the conductor because they will still experience an attractive force from the remaining negative charges. And same way, if these excess charges are negative, they cannot move outside the conductor because of the remaining protons from the solid conductor. So In other words, they will remain intact on the surface of the conductor. During electrostatic equilibrium, these excess charges will accumulate on the surface of the solid conductor. Now, if I try to calculate the electric field inside a conductor using Gauss's laws, I'm going to draw a Gaussian surface inside the conductor. So based on Gauss's law, if this is my Gaussian surface and there's no excess or net charge inside this Gaussian surface, then this enclosed charge is equal to 0. Therefore, the electric field inside a conductor or solid conductor is 0. But what if I focus my attention on the surface? So for example, if I try to draw a Gaussian surface on an infinitesimal portion of this conductor surface, so if I try to zoom it here, basically if this is the infinitesimal area dA, and it has an area vector that points in the direction of n hat. And obviously, since the electric charges accumulate on the surface, it also produces an electric field that is parallel with the normal vector of the area. So when we have a surface charge, we can use the concept of surface charge density to calculate for the magnitude of the infinitesimal charge. So for example, I have an infinitesimal area of dA, then if I want to calculate the total charge of this infinitesimal area, I just have to multiply this with the surface charge density to calculate its charge. So using Gauss's law on this infinitesimal area, electric field times the infinitesimal area dA is equal to the enclosed charge, which is dq, divided by epsilon naught. But notice that dq is equal to sigma times dA divided by epsilon naught. And based on this infinitesimal area cancels out, and we are now able to derive an expression of the electric field on the surface of the charge, which is equal to sigma over epsilon naught. Now, in vector form, electric field is equal to sigma over epsilon naught, and its direction is obviously normal to the surface. It is perpendicular to the surface, because if it's not perpendicular, for example, it has a component that is also parallel to the electric field, then obviously the charges will move along the surface. And in electrostatic equilibrium, we assume that the charges are not moving. So basically, this electric field must not have a component that is parallel to the surface when we assume electrostatic equilibrium. So this is the electric field on the surface of a conductor. As a practice problem, you can try to calculate the electric field of a charged solid conducting sphere with radius r and total charge q. If you want to calculate the electric field at points inside the conductor, that is at a distance r sub 1 from the origin, if you use Gauss's law, then you'll find out that the electric field is equal to 0 inside a charged solid conducting sphere. If you want to calculate the electric field outside the solid conducting sphere, for example at point P with a distance r sub 2 from the origin of the sphere, then using Gauss's law, you'll able to get an expression for the electric field that is equal to 1 over 4 pi epsilon naught q over r squared, which is the same as the electric field due to a point charge. Finally, if you use Gauss's law, you'll be able to derive an expression for the electric field of a solid insulating sphere with charge q that is uniformly distributed throughout the volume. So again, unlike a conducting sphere, we know that the excess charges usually accumulates on the surface of the conducting sphere. But in an insulating sphere, the excess charges can be actually uniformly distributed throughout the interior of the volume. So again, if we have a solid insulating sphere with radius r and total charge q, if you wish to calculate the electric field inside the sphere, for example, at point P with a distance r sub 1 from the origin, you'll be able to derive this expression. 1 over 4 pi epsilon naught times q times the radius or the distance of that point divided by r cubed or the radius of the insulating sphere. And similarly, if you want to calculate the electric field outside the insulating charge sphere, you'll have an expression similar to the electric field due to a point charge. Let's try to answer problem 43 from OpenStax University Physics Volume 2. So in this problem, a very long thin wire has a uniform linear charge density of 50 microcoulomb per meter. We are asked to find the electric field at a distance 2.0 centimeters from the wire. So we already derived the electric field for a thin wire using Gauss's law, and it is equal to lambda over 2 pi epsilon naught 1 over r hat. So plugging in the numerical values, electric field equals lambda is equal to 50 microcoulomb per meter. 50 times 10 raised to negative 6 coulomb per meter divided by 2 pi times epsilon naught, which is the permittivity of free space, and it's equal to 8.85 times 10 to the negative 12 c square over Newton times 1 over r. We wish to calculate the electric field at a distance 2.0 centimeters from the wire. So that would be the value of r. So 2.0 times 10 to the negative 2 meters r hat. So this is equal to 4.5 times 10 raised to 7 Newton per coulomb. So that's it. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching.